Thank you so much for the kind introduction. Good morning, everybody. Thank you to the workshop organizers for the kind invitation, and it's a great pleasure to be here. Today I'm gonna introduce some of our research work. Related to long-term human motion prediction, but many including this upstream task perception and downstream task navigation. And then let's see how to connect these two three together. So let's start with the ground vision. So our ultimate goal is to deploy these mobile robots seamlessly into dynamic human-centered environments, like the airport, hospitals, and the site workers, and so on. As you can see here, this is like a trash robot currently deployed now at the Paris airport, and some of you might have already seen it. The biggest challenge here is actually not the static structures. It's actually us, human beings. We are faster, dynamic, and sometimes unpredictable. So to operate safely and efficiently, our robot must anticipate what people will do next, and this make a long-term human motion prediction one of the key technologies for this proactive autonomy. So before we dive deep, let's clarify what we mean by long-term. So short-term prediction usually looking 1 to 2 seconds ahead is largely this physical-based and linear is meant for immediate collision avoidance, right? Instead, long-term prediction extending up to 10 seconds or more is a different beast, which is highly non-linear, driven by human goals, and depends heavily on this spatial context, which is really crucial because it gives the robots the necessary time horizon to plan smooth and natural trajectories instead of executing jerking and emergency stop. In reality, this long-term human motion prediction does not exist isolation. It actually sits in the middle of the autonomy pipeline, right? As you can see here, it takes input from upstream perception modules and provides output to downstream navigation and planners. So the reality is that the success of prediction can be bounded by this quality of perception, and its practical value might be realized only if the navigation system can actually execute based on these predictions. This brings me to the key words of my talk, which is Sandbox. The question here is how to get everything actually well linked. So my argument actually includes 3 aspects. First, to better build these predictive models, we need data, which come from the perception, right? Second, to demonstrate the value of predictions, we need to deploy the model. Finally, to better evaluate this long-term human motion prediction, we should integrate it into different real robot systems. Here's the outline for the rest of my talk. First, we will explore some realities of upstream perception, specifically focusing on 3D LiDAR. And secondly, we will briefly touch upon the core mechanisms of long-term human motion predictions and how it acts as a bridge. Then third, we will discuss downstream deployment and what it means to navigate according to social norms. Finally, we will wrap up by looking at the integration requirements for true long-term robot autonomy. So when we talk about this robust perception for mobile robots today, I think 3D LiDAR is frequently mentioned. It actually provides accurate matrix spatial awareness and up to 316 degrees field of view. And most importantly, for long-term deployment, it is impervious to these lighting changes. And this makes it the ideal sensor for large scale, long distance, and long-term human detection and tracking. So, sorry. Okay. To understand why we focus on LiDAR, let's briefly compare it with another mainstream sensors in mobile robotics, which is this RGBD camera. And this video shows how we project YOLO-based 2D image detection into 3D. And as you can see here, although the prediction is pretty well, but it still has some limitations in both not prediction, detection, right? In both breadth and depth. So for long-term predictions, we prefer this complete trajectory data rather than just a segment of it. Of course, LiDAR also have some limitations which we want to discuss here due to time constraints. So the upstream perception pipeline can be further break down into two steps. First is detection, which is to sift through hundreds of thousands of this point cloud to identify the specific clusters that represent human bodies, right? Second is tracking, which is to link these detections frame by frame to create continuous trajectories over time. And these trajectories are the fuel for these long-term human motion prediction models. And most importantly, if perception pipeline provides broken or noisy trajectories, then the prediction model will struggle to perform well, right? So what are the challenges we have with LiDAR? I would say the first major issues issue here is the disparity with distance. For example, a person 3 meters away might yet 300 points, which is okay and allows us to clearly define their shape. But at 20 meters, we might only get 50 points also. And this is no serious problem because the long-term prediction requires understanding the people before they get close, right? So the second major challenge is occlusion. This problem also exists widely in cameras, but it's more actually complicated for LiDAR. For example, when a pedestrian disappears from the LiDAR's view and then reappears, the lack of this easily interpretable, understandable information such as the texture and the color makes it difficult to re-identify the person from the point cloud data. So for long-term human motion prediction, this fragmentation means the model either has to guess where the prediction, where the pedestrian went, dealing with this so-called ghost tracks, or it has to wait to for the trackers to reinitialize, which resets the historical data needed for long-term forecasting. So the third challenge is ID switches. In my opinion, so in crowded spaces, when two people cross paths, the tracking algorithm might confuse them sometimes. For example, we might see that person A suddenly inherits the historical trajectory of person B. And from the perspective of this prediction model, this problem severely actually breaks the temporal continuity, which leads to catastrophic prediction failures. So to summarize part one, I think in order to issue the quality of this long-term human motion method development, instead of having the robots learn online, our previous approach was to first collect point cloud data and then generate these human trajectories offline for predictive model building. And this the point cloud data can be either from the robots, first person perspective, like the upper images showed, and or from a third person perspective provided by LiDAR placed in the environments, like the bottom one showed. So now let's move to part two. So from the perspective of this conventional robot navigation, we can divide. We can divide the prediction into two levels, say global and local. So globally, we hope that the robots can arrive at the right location at the right time through prediction, of course. Here, the left and the right side correspond to the data usage of the two data collection scenarios we just showed. So the video on the left shows the 24-hour movement of people in the corridor of the Lincoln Center for Autonomous Systems, where I previously worked, summarized by a spatial temporal model. And this model can be used to guide the daily movements and the work area of mobile robots. So the image on the right actually shows a experimental setup with a spatial temporal model. Another one built using months worth continuous people movement data collected by the LiDAR placed in the environment. So this actually a model was used for the robot time-based decisions regarding avoiding clouds when patrolling between these 3 points, point A, B, and C. So locally, robots with long-term prediction capabilities are expected to exhibit more comfortable movements for humans. So early methods employed bottom-up modeling approaches, such as using constant velocity model to predict human movements. And later, many data-driven methods emerged to address the diversity of human movements. And even recent methods utilize this deeper reinforcement learning to balance the complex interactions between different pedestrians. So our recent methods, as you can see here, combined this traditional linear prediction here and with this modern learning techniques. On the other hand, predictions must be physically grounded, right? So by incorporating this static map data, we can teach the models about environmental semantics and these affordances, like where the corridors and doors are and their uses. So for example, the left side shows the environment of the data set we recently collected, and there are 2 doors there, and with a small door for pedestrian to enter and exit. So this one, and a large door here for this different vehicles to load and unload. So understanding the difference between the two is expected to improve pedestrian prediction value, right? However, encoding this rich map data efficiently, especially without causing this latency spikes in the prediction inference loop, still remains hurdles in deployment. So this is a sample of our novel data sets which is a data set of socially compliant and no compliant robot navigation, of novel robot navigation. So as you can see here, the data set contains data from multiple modalities to describe the robot's perception of static and dynamic objects. It also includes accurate trajectories of human movements extracted from this environmental 3D LiDAR data. And we can also see the map and some color and texture information, especially generated from this RGB camera, also provided to help us to better understand the semantics of the environments. So this leads us directly into part 3, which is this downstream navigation. So the question here is, how can we take these predictions to enrich this human-aware navigation? So one possible answer here is to make a robot navigation conforms to social norms that cover several aspects. So first is this spatial distance, meaning respecting personal space and avoiding getting too close to humans. And the second is this directional preference, such as the rule of vehicles driving on the right in many Western countries and driving on the left in the UK, in Japan, etc., etc. So third is this speed matching, because robots moving too fast or accelerating suddenly might startle people, right? Finally, it's respecting the group. So if several people are walking and talking there, the robots should then walk around rather than walking through this group, right? So here's image on the right. This one shows actually several social scenarios recorded in our data set and novel set. And specifically, these scenarios were recorded separately and independently rather than conjointly like the other some other data set, let's say. Meaning our data set contains explicit this social and semantic labels. Then I think the very next logical question would be, how do we technically achieve this human-aware navigation or even social-aware navigation? So our recent approach involved using a navigation module based on deep reinforcement learning to first establish the basic pipeline between perception and self-control, and then use a social module based on a lightweight network to perform a social evaluation online on the control output of the former module. So let's say if the output provided by this navigation module is deemed not social or less social, then this social module can modify or say adjust this output and make it to be social. So here let's take a look at this practical effects. Here ORCA, ORCA is a classical navigation method without human awareness. And so SARO is actually our method which can show pedestrian avoidance behavior early enough, making human more comfortable, right? So in reality, this human-aware navigation is also kind of human-robot interaction, and not only it's usually no contact, or sometimes we say implicit. So this interaction gives rise to the concept of this legibility, right? Just as we run complex neural networks to predict human on our robots, the human is also actually using their very smart brain to predict the robots in turn. So legibility means that the navigation stack shouldn't just find the mathematically shortest path, but also find the path that clearly communicate its intent. So sometimes slightly show a turn, for example, action early enough helps the human understand the robot's goal, and then smoothing out the whole human-robot interaction, right? So this has been well proved in our previous work. If you're interested, please check out our paper. And on the other hand, evaluating the human-aware navigation performance is a challenge. Existing metrics can be more or less categorized into subjective and objective perspective. And the subjective metrics are typically in the form of questionnaires, which objective ones usually refer to roles that we can actually calculate, right? However, currently using different metrics often yet different conclusions, especially when evaluating different methods. Therefore, we need some new ones, right? Moreover, how to identify the correlation between subjective and objective metrics is also a topic worthy of in-depth exploration, in my opinion. So our recent work proposes this human in the loop evaluation method. The idea here is to compare human control and algorithmic control, much like you play a game, and then use this kinematic matrix to evaluate the robot's navigation performance. So the last question here is how we really implement navigation sandbox for long-term human motion prediction. So as common planners optimize paths based on coastal maps. So we might want to integrate this long-term human motion prediction by projecting our probability distribution into a feature and a time layered coastal map. For example, if the model predicts someone will occupy a specific area in 3 seconds, say, then we can increase the cost of that area at a specific feature time step. So this mathematical constraint allowed the planner to calculate proactive detour routes we are aware before an actual collision in imminent. So this brings us to the final part of our journey. This system integration. Say, how do we put everything together? Nicely, right? So based on our experience, the most prominent system requirement is manage the trade-off between latency and accuracy. And we know very well that long-term human motion prediction models need to account for faster-moving robots. So like we often said, within half a second, a human might have already moved, and the robot's prediction becomes outdated. So we must optimize, to achieve a trade-off between model capacity and inference speed. In our previous work, we basically rewrote the original CPU-based code with CUDA-based one for these edge devices, especially this NVIDIA based devices. So, but for sure, there are other optimization methods which we can, of course, discuss offline if we are interested. Furthermore, we emphasizes closed loop real world testing. Here, I mean, simulations are excellent tools for sure, but they struggle to capture the nuances of human psychology, such as eye contact, hesitation, even social praise. Pressure. Sorry. So to truly validate this long-term human motion prediction, we might want to run the complete process, including perception, prediction, and navigation, using this physical hardware, where in real-world settings such as public shopping malls, airports, hospitals, or at least our own offices, right? So as I look forward, I see several open challenges for our community. First, lifelong learning. I often say, a robot in the hospital should gradually learn the specific shift patterns and habits of these doctors, nurses, etc., etc., rather than solely relying on a static pre-trained model. And the second, we need more data sets, as always, that record actually close the loop interactions between the robot and the humans. And finally, this explainability. So when deployment fails, we must be able to trace back whether it was a prediction, perception, blind spot, or a prediction, hallucination, or even a planner value. That concludes my talk. Thank you very much for your attention. And I'd happy to take any questions you might have now. Thank you so much.
Thank you very much. So we may have time for just like one question, and its next speaker can come and just start setting up. That would be great. Thanks. Okay, any questions? I think Dian has done a lot of down to the earth work on social navigation, so covering many different aspects. So if you have any questions, I think it's a good opportunity to ask. Good. All right, yes, go ahead.
So thank you for your nice talk. And I have a question. What's your opinion of the difference between like a robot human interaction and human interaction? Can we treat the robot as a human when doing the prediction and planning for the robot? That's my question.
Okay, that's a really good question. I think currently, my personal opinion, we cannot really treat robo-human interaction and human interaction as the same thing, because obviously the motion pattern also the movement style of robots and human, they are obviously different. I think still people must be aware about this human robot motion patterns, like suddenly sudden stop or fast acceleration, etc., and to react early enough to avoid any collisions with the robots. Of course, sometimes people might say, probably the robots might just stop there in order to wait us as a human beings to react first, also to pass first. It can be, but not always the case. So we should at least for now clearly distinguish these two interactions. Yeah, that's my opinion. Thank you.
Okay. Yes.
Thank you so much for your interesting talk. I have a question, but actually it's for you, but also for Kathy. In both of your works, you haven't touched this new trend of Gen AI, right? Foundation model, vision language models, VLAs, and so on. Is there a particular reason? Is there, you're not trusting this embodied AI subfield, or you're starting to work on this? It's an open question. I'm more a curiosity-driven question. Yeah.
Okay. So thank you very much for your question. Maybe I go first. Okay. Thank you. So to be honest, it's not really my case, at least for my today's talk. I have some ongoing work with water model, VOA. I think one of our motivations is to see how could leverage is modern technology or say up-to-date method to explore a little bit the potential of this human-aware navigation, or see if we can really push the performance boundary a little bit forward, but we are still unsure. From my personal opinion, we still believe the classic or traditional, especially mathematical-based method, at least to ensure the minimum safety of the robot movement. That's my opinion. Thank you very much.